Moment. All right. Good evening, everyone. My name is Akash Vidyadharan. I'm a research assistant at the St. Louis University and a PhD student. And my topic is an investigation into the autonomy levels across Telerobot platforms with and without manipulators. So just to introduce, telerobots are equipment that extend a user's presence remotely in environments that they can't physically reach. An important component of telerobots is social presence, which is a gauge of feeling of presence of an entity in an operation environment. There are two types of users in a usual telerobotic setting or in the environment. One is the pilot user who controls the telerobot interactions from an input mode like a laptop or a gaming or using a joystick. And the second is the local user who engages with the telerobot in the environment. So just for a background, initial telerobotic systems which were developed earlier, like the NASA's Robonaut and the Da Vinci surgical system that you can see right here, were primarily task-focused, not much social presence programmed into it. Moving ahead, systems such as the Vigo and double telerobots, as you see in the center of the screen, were built for presence in classroom and healthcare settings where social presence was an important factor. And moving ahead, the Casper robot that you see right here on the table included head gestures and speech, which were verbal and nonverbal cues, which research has proved that it helped improve user engagement. Now, with the advent of AI, computer vision, and autonomous navigation, it's helped to make dynamic and responsive interactions between telerobots and pilot users and local users as well. While past studies have focused either on autonomy levels or on nonverbal cues in isolation, our study investigated the combined impact on the task performance and social presence. So the primary challenges, as we mentioned, were conveying nonverbal cues such as gestures, facial expressions, using arms manipulators as well, and also the lack of feedback and social connection from the pilot and the local user perspective. So the two research questions we framed out of this were, how do varying levels of autonomy, 3 levels, autonomous, semi-autonomous, and manual, affect the task performance efficiency and user experience during social interactions and navigation with telerobots? And what are the impact of manipulator arms on the pilot user's experience, primarily on task performance, ease of interaction, and a sense of social presence? So for this particular experiment, we used two platforms, Temi, which is a commercial off-the-shelf robotic platform which came with its own SDK or software development kit. And as you can see on the left, has no arm manipulators. And on the right, we have Quarry, which is a research robot, which has 2 degrees of freedom arm manipulators, runs on Ubuntu, programmed on ROS1 using Python by me. And we programmed it in 3 autonomy modes. The manual mode, in which a pilot has full control over the base and manipulator arm movements. The semi-autonomous mode, where there was shared control between the robot and the pilot user. And a fully autonomous mode, where the robot operated independently without the pilot, except for verbal cues and verbal interactions. Both robots had a standard GUI element for control. So it included a video live stream, a sequence of tasks to be performed in the operating environment, and similar controls mapped on keyboard and computer vision. So there were 3 autonomy modes as mentioned earlier, and 2 different types of tasks. The navigation task, where the pilot user had to navigate the robots from point to point and perform interactions, and the interaction task, where the pilot user had to perform verbal and non-verbal gestures. For the manual mode, for navigation tasks, the pilot user had full control of base movement using arrow keys. For semi-autonomous navigation tasks, the robot was programmed to follow predetermined paths, and the pilot user would initiate transitions between the different interaction points. And in fully autonomous mode, the robot would navigate autonomously on predetermined paths and automatically stop at interaction points in a timed manner and move on to the next. For interaction tasks in manual mode, the pilot manually performed all interactions, gestures, and voice using manipulators. And in semi-autonomous mode, the pilot managed rotations or adjustments of the robots in these interaction points and also used his voice and performed semi-automated gestures using computer vision controls. And in fully autonomous mode, the robot performed manipulator interactions by itself, and the pilot user only performed verbal gestures. So on the right, you can see the Quarry's control system architecture. For the technical development and contributions included the programming of 3 different autonomy modes for both Temi and Quarry in navigation and interaction tasks. In terms of connectivity, we used a local Wi-Fi network for video live stream and control transmission for Cori, and also a custom UI with video live stream control mode, as well as the manipulator arm position, which could be controlled using keyboard as well as computer vision. We created two computer vision models, one for semi-autonomous mode, where it was gesture pose estimation based on fingers. And the second one was the manual mode, where it was a virtual joystick based on computer vision with arrow keys overlaid on the webcam view. The research study involved 30 participants where 80% were male with a mean age of 26 years, and all participants were tech proficient with a bachelor's degree or higher. The entire study for each participant took 90 minutes, where there was a training phase where they were familiarized with both robots and the three different autonomy modes. As mentioned earlier, the experimental tasks involved both navigation and interaction tasks in an office environment, where the interaction tasks included a greeting, object referencing, and attention gesturing from two local users in the environment, and this was performed in all three autonomy modes. So here's an overview of the study environment, where the X point on this map in the room denotes a starting point. The robots would navigate to point 1, face the first pilot user, wave and perform its verbal gesture, move to the second point, point at the object of interest to the local user with a verbal speech, and then move to the third point, face both local users and gesture for attention verbally and in terms of Cori with its arm manipulator as well before returning to the home point. For the interaction task overview, as mentioned earlier, there were 3 interaction tasks. For greeting, pointing, and alert, Temi only used, the pilot user only used voice messages on Temi, while for Cori, all 3 modes had the pilot user use their own voice for communication, and the manipulators were used to perform wave, pointing, and raising both arms for alert. For the data collection analysis, after each participant did 6 trial runs, 3 for each robot, 3 autonomy modes for each of the robots, metrics were captured and analyzed. The task completion time, stalls, deviations, and accidents for each of these, for each of the robots and 3 autonomy modes were captured and recorded. And from the user perspective feedback, post each task, a systems usability scale, a user experience questionnaire, and a NASA TLX questionnaire was provided, and the users had to provide their feedback. Here you can see the UI of Cori, where computer vision was used for arm manipulation. Based on the result, once we obtained the raw data, within subject ANOVA analysis was performed, which showed higher autonomy, improved navigation speed, and reduced deviation and stalls. Temi, which did not have arms, consistently outperformed Cori in navigation times as well, and higher autonomy improved interaction task performance. Furthermore, it was found that Cori's manipulator did add complexity due to the method of input using computer vision, which increased the task times, and Temi scored higher on usability. Furthermore, Temi showed lower workload scores, indicating lower mental and physical demands. The chart on the right shows Temi's and Cori's mean interaction task times in manual, semi-autonomous, and autonomous modes, respectively. And from the results, it was found that SUS and UEQ scores were higher for Temi. Temi surprisingly rated higher for social engagement as well, although it did not have manipulators. Temi had lower task load in all control modes, and the autonomy significantly impacts efficiency and usability. And simplicity and form factor of the robots did show better engagement in this experiment. For future work, we intend to explore optimal controls for manipulators and understanding how to increase social presence using different types of control inputs. I'd like to acknowledge all the study participants involved in the study team, Dr. Mitsuru Shimizu for his support in data analysis, and the Cori Award Program and the St. Louis University for funding, equipment, and the study. Thank you. Now I'd like to open the floor for questions and comments.
Thank you, Akash. Any questions from the audience? I have one comment. It seems counterintuitive that when you don't have waves, you don't have the robot waving at you, that you had higher engagement. Do you have some explanation as to?
Yes, there were 2, and this is actually what the next study is about. So the first issue is that, or the first point I would like to say is that this is from the pilot user perspective. So when there are no manipulators to control, they probably felt that it was easier and felt that social presence was lower with Quarry. Second one, based on some interviews that we conducted, the computer vision mode of input was hampering their ability to communicate properly. Therefore, we plan on testing it with joysticks and keyboard inputs as well, and comparing the three to make sure that we do have the best method of control input for Quarry, and to see if that would help improve the social presence or the interactions with the Telerobots.
Okay, wonderful. Thank you.
Thank you.
I don't know if you can see us or not, but we're all waving. We're all clapping for you.
Oh, thank you.